Let's turn ideas to action together. So myself, Shamchandra. So this is the agenda for this session from 3:30 to 4. So the challenges faced from the fluid and valve industries. So mainly in the fluid and valve industries, we have a lot of flow conditions and variable parameters. For example, the input may be in a flow rate and output we need to calculate the pressure losses. And in those conditions, we may find difficulties how the pressure flow is going on and where is any turbulence is happening. And especially if we come to other kind of valves which includes a mechanisms, then it will be difficult to predict or imagine the flow conditions and flow parameters. Apart from all this, the valve may also experience uh, load conditions due to the flow rates, and also the right amount of temperature distribution from the fluid to the valve or from the ambient to the fluid may happen. So for this kind of issues, currently in industry we have a traditional validation process where we go for a lab setup or a hand calculation. Through lab setup, we will set up all the component, a valve in this condition, and we will set all the sensors. For example, temperature sensor and load sensors, everything we will fix, and we'll give the input flow conditions, and we'll get a graph like this. And this is a very complicated process where we need to set up all the conditions. We need to integrate the sensors with computers. So in this traditional validation process, once we design a component, we go for a prototype and we test the prototype in the laboratory condition. So up to its approval process, if there is any compensation, is there any variation in the design model, we will redesign it and again we go for a prototype. So this cycle follows up to the final approval stage. In virtual validation, we can exactly predict where a defect may occur in the model. For example, in this impeller model, the fins are affected due to the cavitation. So this cavitation, we can do it in a CFD analysis and find here is the more turbulence is happening. So the cavitation appearing chances are more high. Through this kind of validation process, without any physical model, from the 3D model itself, we can predict where the pressures are going to be or what are the changes the pressure makes to the components. So from this virtual validation, once we have an idea, we will get a 3D model. Through the 3D model, we can directly go for a validation. From that validation, we can reach the market in a very shorter time. So in the design validation process, SOLIDWORKS has three components. SOLIDWORKS simulation, where it's for finite element analysis. If particular valves need seismic analysis at certain conditions, we can do it with the finite element analysis. And SOLIDWORKS flow simulation, it's CFD analysis, where we can analyze what is the pressure flow inside and out of the components. Then SOLIDWORKS plastic, it's for injection molding of components. So these are the some highlights of SOLIDWORKS simulation. In this SOLIDWORKS simulation, we can do seismic analysis as told before, and we can also do a drop test for the valve mechanisms, and also what will be the mechanism, what will be the rotations in the valves that can be animated, or a kinematic study can be done through the motion analysis. Then we can optimize the valve with the optimization tool, where we can reduce the valve weight, or we can also reduce the valve stress level by setting a goal condition. So these are the some highlights of SOLIDWORKS simulation. And here the SOLIDWORKS flow simulation. In SOLIDWORKS flow simulation, we can do both the internal and external analysis for the components. Then on top of it, we can do electronic cooling model. In this electronic cooling is specific for electric industry, where they have PCB control boards and other PLC boards. Then we can do an HVAC analysis for an entire building or component rooms. So these are the some highlights of SOLIDWORKS plastic, where we can do the molten plastic flow conditions in and around the mold. So this is the flow simulation model capability. So in flow simulation, as we discussed, we can do the internal analysis for walls, then also an external analysis for a kind of an airfoil structures here. Then a specific study for rotating impeller component is here. So through this study we can design an impeller fan blades angle and what is the optimum angle to get the efficient flow rates can be analyzed here. Then we can also do a result exchange. Once we do a CFD analysis, that results can be imported to FEA analysis to predict what is the pressure around that component due to the flow conditions. So these analysis will be detailedly seen in the upcoming slides. So this is SOLIDWORKS Flow Simulation. Why we need to go for a SOLIDWORKS Flow Simulation? Through SOLIDWORKS Flow Simulation, we can really eliminate the critical problems in the flow industries. And we can also analyze what is the temperature distribution around the components with the simple 3D components. And these models are 3D integrated. So once we design the model in the same interface, we can go for an simulation analysis, both FEA and CFD. And we have advanced analysis tools like parameters where we can do valve optimization. So we can design what will be the valve opening so that we can control the pressure or velocity of particular conditions. And with SOLIDWORKS Flow Simulation, we can automatically easily generate a flow report. Through that flow report, we can get what are the input conditions we have given and what are the output conditions we are going to get. So this is the sample model, a ball valve which has been taken for this today presentation session. So in this ball valve, we are going to do an flow simulation, and we also import this flow simulation result to an FEA to analyze what will be the working pressure on this component and whether this valve can withstand the burst pressure of the simulations. So in SOLIDWORKS Flow Simulations, we have these 5 setups. So whatever the analysis, these initial 5 setups we are going to define it, and in the upcoming models we're going to see how easy it is to define those flow conditions and how to easily get the results, and we can in what and all ways we can going to interpret those results for our further study and further analysis of this model. So so once we have done the model, we are going for an project setup in a simple wizard based model where we are going to define what will be the fluid conditions, what are the basic input parameters. So let me show it in the model. So here is the SOLIDWORKS window. In this SOLIDWORKS window, this is the design window where once you design the component and assembled it in a 3D model, you can directly go for Addons, and here you see SOLIDWORKS Simulation and SOLIDWORKS Flow Simulation. So here just click it and we get a separate tab here for the flow simulation. So once we get a separate tab for simulations and flow simulations, we are good to go to do the simulation analysis in the same interface. So I'm going to choose the flow simulation and I'm going to click the wizard where we can define what is the project going to be. So I define project value. Then we can also define various conditions. For example, what are the configuration? In the same valve model, we can save multiple CAD data with minor changes. So that won't take much data storage for the single data. In this model, a single CAD data can be drawn or developed in various conditions. So we can all include in the same CAD file. Next is defining the units. In this model, we can define the SI units, or we can also changes can be done, like we can change this condition to various condition, like for example here I convert to Pascal to bar, and it can be saved as a separate model. For example, in any industry they're using any kind of specific units for their analysis, we can create a new one and we can define the company name for it for our further study references. Here we need to choose the model is going to be an internal or external analysis. As it is a wall, we're going for an internal analysis, and here are the conditions like whether we are also going to do a thermal analysis like conduction, convection and radiation. Then time dependent condition, for example, what is the temperature varying according to the time dates, that can be defined here, and the gravity conditions to imitate the real physical conditions. So here we are going to choose the fluid conditions. For example, if it is gases, all the gases properties are predefined in the SOLIDWORKS Flow Simulation library, and the liquids, non-Newtonian fluids, all the databases are available. We can also customize these data by adding the particular material property to it. So here I will choose water for sample. Then these are the valve conditions. We have any kind of adiabatic valves conditions, we can define it here. So by clicking finish, we come to a new window. So through this wizard based option, we can initially set up the basic inputs for the condition. We will provide what are the fluid properties and what are the valve conditions for this particular model. Boundary conditions, the real-time behavior of this model. So boundary condition, what is the pressure inlet and what are the pressure outlet will be defined it here. So in this model, we defined an inlet mass flow of 0.2 kg per second and the outward is an environmental pressure. So these conditions can be easily defined and the parameters can be changed, and we can also define the any kind of thermal parameter can be easily defined it here. So if we want to consider an initial temperature of the fluid will be at 100 or 200, we can directly define it here. So setting up what is the fluid going to be flow at what rate, those conditions will be initially set up in the boundary condition parameters, and other conditions like what will be the initial pressure, what will be the outlet pressure, assuming it, or the initial development stage conditions can be defined it here. Then goal setting. In the goal setting, we are going to choose what are the parameters we want to analyze in this valve model. So that will be defined as a goal condition. So here there are a lot of goal conditions like global goals, surface goals for our specific needs. Here in this global goal, I will choose what is the total pressure in this model, and I can choose the minimum, average and maximum. Then I also choose what will be the mass flow rate or what is the velocity of the fluid here. And if I define any kind of temperature, I will define what is the temperature variation in this model. So these values can be defined here. Then we can also define an equation goal. An equation goal is nothing but we will form some equation. For example, here I want to calculate what is the pressure loss. So I will define the outlet pressure minus inlet pressure, or we can, if you want to calculate the CV, we can define it conditions. We can also include integral values and logical operations can be included here. So once we define the goal conditions, these conditions will be helped while compiling the results. So if we want to take a set of data and we want to interpret it, these goal conditions will be very helpful for that. Then meshing the model. So as it is, meshing is for a 3D model is understandable for a human being. The software need to understand this model. So basically for that we are going to do the meshing. So in this mesh model, I need to define what are the conditions. So here we have both automatical and manual meshing. So in this meshing we are going to define what are the parameters, like what is the fluid region will be and what are the solid region will be, can be defined here. For example, I want to show you how efficiently we can mesh these models. So this is the cut sectional view of this model. We will see what is the meshing here. So this is the mesh rate, we define it here. So this red regions are finer mesh and the blue regions are coarse mesh. In the red region, the finer mesh, the result will be compiling more compared to the blue region where it is coarse. And this can be optimized, or this can be set according to the fluid complexity or the model complexity. For example, this is the mesh we have done here. Now by loading the result, we will get the detailed mesh value or the mesh model of this component. So this is the mesh of this wall. So here there are very fine meshes, this red regions, compared to here this is very coarse, because the inlet fluid will be very critical at the ball wall mechanism region. So in this mechanism region, if you saw the layer, there is very fine mesh. To compile it in a very accurate manner, we have this kind of advanced meshes. So this mesh, we can get it to a very advanced level, like we can go for adaptive meshes. In adaptive meshes, the mesh will be automatically vary according to the flow rate and flow condition regions, and we can also predict local mesh conditions. So what does local mesh condition means? We can mesh a particular region. For example, it may have, the wall may have any kind of sharp regions, or a region where the fluid contact will be more higher and more turbulent. Those regions we can define a local mesh. So then after we all setting it up, we can directly run the model and we can see the result. So here, once we compiled, we can load the result and we can see what are the data we can interpret it. So first here we have chosen a thermal temperature. So the thermal temperature is actually given for one particular side of the wall. So here we are given thermal temperature. So for this wall, we are given a particular 1000 watt. So through this 1000 watt, we are going to see what is the temperature variation or temperature distribution to the walls. So this is the temperature distribution. As the wall getting heated by 1000 watt, the fluid is not get affected much because these wall regions are so thick. Then by seeing the velocity, we will see what are the ranges here and what is the velocity distribution over particular regions, because here this region we have the valve opening, so the velocity is critical here, but the velocities are bit finer or bit laminar kind of flow here in these regions. So these laminar or turbulent can be seen with a specific graph. So we can choose these various parameter. So here I want to see what will be the turbulence. So I am choosing turbulent intensity and seeing here. So this wall has a turbulent intensity over these regions. So once we see what are the various flow conditions or a parameter in the wall, then we can also see how the flow pattern is. So how the flow is flowing over the wall, over the mechanisms, like at each opening, how it is flowing, whether it is 90-degree or whether it is 30-degree opening, how the fluid is going to behave according to this kind of variable mechanisms. So once we have done this, we can get a goal plot. So here whatever the goals we chosen in the goal plot will be displayed, and we can see what are the values, and these values can be directly exported to Excel, Microsoft Excel, where these data can be do for further report submissions, and we can also see it in a graphical view. So once we got these results, we can export this model as an e-drawing to further customers or further higher authorities for referring it and for the approval process in the initial stage of the design. So once we have done this CFD analysis, we can input the study to FEA. So after the study has been done, I'm just going to the model back, and here I open the simulation study where I can choose this list of studies available. So initially I'm going to choose the static analysis. In the static analysis, this will be the parameters, like we need to define the material of the component and same as the boundary conditions and fixtures. Then we need to mesh the model and we can see the results. So now the material property can be given directly. So these material property are available inbuilt in the design library data. So once we choose the appropriate material, we go for the fixtures, that is a boundary condition, where how the valve is going to be mounted. That condition we will given in fixtures. Then we directly import the CFD results through flow effect option. Once we click this option, this flow effects will be automatically imported and we can define the thermal conditions here. In this thermal conditions, I will define whatever the thermal condition is applicable. I just load the file directly from here. I will just choose the appropriate file folder and the file study. Then for the flow condition, I will choose in here. So the result. So this is the stress level induced due to the flow conditions, due to the flow parameters. Now, like this, we can also go for a dynamic analysis and optimization and flow simulations. The optimization analysis can be seen more detailing. So here we are going to define a variable conditions and a goal conditions. In the goal conditions, the main goal is to reduce the weight of the component without compromising any kind of working efficiency. So we will choose what are the parameters we want to reduce, or we have the freedom to reduce, for example the outer diameter or the thickness of the wall conditions. If we have the freedom to change, we can define it as a variables. Then in the goal condition we can choose either the stress level or the weight of the component. So once we're chosen, we'll automatically get the optimum result and also the various multiple iterations. We can choose the best out of it. So in summary, if we take a wall and we design it in the initial stage to the advanced level, we can do all kind of complex analysis like from the CFD to FEA in a single interface, and we can visualize what will be the flow around the component, and we can use a goal study to optimize the wall in various possible conditions, and we can also predict what will be the functioning capacity, the life of the component. The overall benefit will be, by doing this virtual validation, we can eliminate the prototype cost and the time taken for developing that prototype and testing that prototype. And this is not a single time process, because after any kind of correction, again we need to go for a prototype testing. So it will take more time and much cost. So through this process, through this virtual validation process, we can eliminate this kind of cost and the time we taken to release the component to the market. And we can improve the quality of the component by predicting what are the various defects may occur in the component in future or in the working conditions. With all these options, we can be the market champion, or we can win the market with full business model. So these are our some of our customer case study. This is a Severin Glocon company. They had any challenges of calculations. They did a hand calculation and they need to go for an which I mean testing of this valve. So they used SOLIDWORKS Flow Simulation and they got benefited. So they stated that the development process has been reduced up to 20 percentage. They reduced from the overall, they reduced 20 percentage of their development time, and they realized what are the problems or fluid condition inside the valves will be, and they also increased the productivity by 46 percentage by cutting down the testing costs. These are the EGS customers in valve industries. These are the global customers for valve industries SOLIDWORKS have. Thank you, ladies and gentlemen. Is there any query? Kindly feel free to contact us. Thank you.